Preface. Civil engineering is an exciting combination of science, art, professional skill, and engineering achievement, which always has to rely on the ground on which its structures stand. Geology is therefore vital to success in civil engineering, and this book brings to the reader those many aspects of the geological sciences specifically relevant to the profession. This book is structured primarily for the student of civil engineering who starts with no knowledge of geology but is required to understand the ground conditions and the geological processes which, both literally and metaphorically, are the foundations of these future professional activities. It also provides an accessible source of information for the practicing civil engineer. The contents of this book follow a basic university course in engineering geology. The freestanding sections and subsections permit infinite flexibility so that any lecturer can use the book as his course text while tailoring his program to his own personal style. The single section summarizing soil strength has been included for the benefit of geology students who do not take a comprehensive course in soil mechanics within the normal civil engineering syllabus. Geology and civil engineering. The geological environment. Earth is an active planet in a constant state of change. Geological processes continually modify the Earth's surface, destroy old rocks, create new rocks, and add to the complexity of ground conditions. Cycle of geology encompasses all the major processes which must be cyclic or they would grind to an inevitable halt. Land, mainly erosion and rock destruction. Sea, mainly deposition, forming new sediments. Underground, new rocks created and deformed. Earth movements are vital to the cycle. Without them, the land would be eroded down to just below sea level. Plate tectonics provide the mechanisms for nearly all Earth movements. The hot interior of the Earth is the ultimate energy source which drives all geological processes. The diagram shows the rock cycle. At the top left, you can see the weathering. Weathering is the process in which, because of the sunlight, air, rain, snowfall, the exposed, rock mass destroys and breakdowns. When it breakdowns by means of water and the air, it transported towards the depressions, means lowlands. This weathering and transportation process is called the erosion. And then lithification starts. Lithification means the formation of the layers by means of the compaction. Then sedimentary rocks forms. So after the formation of the sedimentary rocks through metamorphism. Metamorphism is the process in which high pressure and temperature applies on the sedimentary rocks or igneous rocks, and the alters. Such rocks are called the metamorphic rocks. And those metamorphic rocks, when the plates, subducts, goes down to the magma, they melts and it forms the magma. And then the magma comes on the surface of the earth by means of the volcanism, and the igneous rocks are formed. And this rock cycle takes more time. It's sometimes millions of years and billions of years to complete this cycle. Significance in engineering. Civil engineering works are all carried out on or in the ground. Its properties and processes are therefore significant. Both the strengths of rocks and soils and the erosional and geological processes which subject them to continual change. Unstable ground does exist. Some ground is not terraform and may lead to unstable foundations. Well, here is a term that is the terraform. Terraform means the solid part of the earth's surface, or the dry land is called a terraform. Site investigation is where most civil engineers encounter geology. This involves the interpretation of ground conditions, often from minimal evidence, some 3D thinking, and the recognition of areas of difficult ground or potential geohazards. Unforeseen ground conditions can still occur, as ground geology can be almost infinitely variable, but they are often unforeseen due to inadequate site investigation. Civil engineering design can accommodate almost any ground conditions which are correctly assessed and understood. Before the construction of a civil structure, we need to consider the geology of that area, some engineering responses to geological conditions. Geology, soft ground and settlement. What you have to do is that foundations designed to reduce or redistribute loading. Weak ground and potential failure. Ground improvement or cavity filling, or identify and avoid hazard zone. Unstable slopes and potential sliding. Stabilize or support slopes, or avoid hazard zone. Severe river or coastal erosion. Slow down process with rock or concrete defenses. Limited scope. Potential earthquake hazard. Structure designed to withstand vibration, avoid unstable ground. Potential volcanic hazard. Delimit and avoid hazard zones, attempt eruption protection. Rock required as a material. Resource assessment and rock testing. Geological time is an important concept. Earth is 4,000 million years old and has evolved continuously towards its present form. Most rocks encountered by engineers are 10 to 500 million years old. They have been displaced and deformed over time, and some are then exposed at the surface by erosional removal of rocks that once lay above them. Underground structures and the ground surface have evolved steadily through geological time. Most surface landforms visible today have been covered out by erosion within the last few million years, while older landforms have been destroyed. This time difference is important. The origin of the rocks at the surface may bear no relationship to the present environment. The classic example is Mount Everest, whose summit is limestone, formed in a sea 300 million years ago. Geological time is difficult to comprehend, but it must be accepted as the time gap accounts for many of the contrasts in ground condition. Concepts of scale are important in geology. Beds of rock extending hundreds of kilometers across country. Rocks uplifted thousands of meters by earth movements. Rock structures reaching 1,000 meters below the ground surface. Strong limestone crumpled like plasticine by plate tectonics. landslides with over 100 million tons of falling rocks, earthquakes a million times more powerful than an atom bomb, and the millions of years of geological time. Components of engineering geology. The main fields of study: ground materials and structures, and we will further discuss this topic in section 2 and 2 and 6. Regional characteristics, surface processes and materials, ground investigations, material properties, difficult ground conditions. Other aspects such as fossils and historical geology, mineral deposits and long-term processes are of little direct significance to the engineer and are not specifically covered in this book. Ground profile through some anonymous region in the English Midlands. Most rocks were formed 200 to 300 million years ago when the area was near the equator in a deltaic swamp distributed by earth movements then left in a shallow sea. The ground surface was shaped by erosion in the last million years when the alluvium and slope deposits partly fell the river Cut Valley. The more difficult ground conditions are provided by the floodplain, soft sediments, deep rockhead, unstable slopes, old mines, and the backfill quarry. Strength of the ground. Natural ground materials, rocks and soils cover a great range of strengths. Granite is 4,000 times stronger than peat soil. Some variations in rock strength are summarized by contrasting strong and weak rocks in the table, which you can see on the left side of this slide. Assessment of ground conditions must distinguish: number 1, intact rock. Strength of an unfractured small block, referred to UCS, means uniaxial compressive strength. Number 2, rock mass. Properties of a large mass of fractured rock in the ground, referred to rock mass classes, section 25. We will further study regarding this rock mass. Note: a strong rock may contain so many fractures in a hillside that the rock mass is weak and unstable. Ground conditions also vary greatly due to purely local features such as underground cavities, inclined shear surfaces, and artificial disturbance. On the bottom left of this slide, you can see strong rocks and weak rocks properties. UCS greater than 100 million Pascal, said to be the strong rock, and UCS less than 10 million Pascal, said to be the weak rock. In strong rocks, little fractures, you can see, minimal weathering, stable foundations, stand in steep faces, aggregate resources, and in weak rocks, fractured and bedded, deep weathering, settlement problems, fail on low slopes, required engineering care. And the picture here you can see is folded rocks exposed along the South Wales coast. In this slide you can see the UCS, uniaxial compressive strength of certain rocks and the soil, and a SBP, safe bearing pressure of certain rocks including the soil. UCS, unconfined or uniaxial compressive strength, load to cause failure of a cube of the material crushed between two flat plates with no lateral restraint is called the UCS. Strong and weak limits are simplified. See section 24 for BS criteria. We will discuss in section 24. SBP, safe or acceptable bearing pressure. Load that may safely be imposed upon rock in the ground. The estimated or measuring ultimate bearing pressure to fail the rock, allowing for fractures and local zones of weakness, divided by a safety factor between 3 and 5. And the left side of this slide, you can see the table where in between there are certain rocks from top to bottom: granite, limestone, sandstone, shale, clay, and soil. If we will talk about the UCS of these certain rocks, you can see the granite is greater than 100 million pascal. Limestone is in between almost 10 to 100 million pascal. Sandstone, you can see, and the soil is less than 1 million pascal. In the same way, if we talk about the SBP, the granite, you can apply greater than 10 million pascal pressure. If you want to construct a foundation upon the granite, you can impose greater than 10 million pascal is the safe bearing pressure with respect to the granite. But for soil, you cannot apply greater than almost 0.1 million pascal. If you would apply greater than 0.1 million pascal, then you have to treat the soil accordingly. Geology and civil engineer, the last slide, which tells us rocks and minerals. What are the rocks? Rocks, mixtures of minerals, variable properties, and the minerals, compounds of elements, fixed properties. Rock properties broadly depend on 3 trends: strength and stability of constituent minerals, interlocking or weaknesses of mineral structure, fractures, bedding, and larger rock structures. All rocks fall into one of 3 families, each with broadly definable origins and properties, such as you can see in the table. Rock family, material origin: igneous rocks, crystallized from molten magma; sedimentary, erosional debris on Earth's surface; metamorphic, altered by heat and or pressure, means when very high pressure and very high temperature applies upon the sedimentary or igneous rocks, they becomes the metamorphic rocks. Second, environment. Igneous rock. In what kind of environment igneous rocks are formed? Underground and as lava flows. Sedimentary rocks environments. Deposition basins, mainly sea. Metamorphic. The environment of metamorphic rocks, mostly deep inside mountain chains. Rock textures. What kind of rock textures does igneous rock have? Mosaic of interlocking crystals. In sedimentary rocks, you can see mostly granular and cemented, and metamorphic rocks, mosaic of interlocking crystals. Rock structure. What kind of structures you can find in igneous rocks? Massive, structureless. In sedimentary rocks, you can see so many structures like layered, bedding planes, etc. In metamorphic rock, you can see crystal orientation due to pressure. Rock strength: uniform high strength, variable low planar weakness, variable high planar weaknesses. Major types: granite. The granite is the major type of igneous and basalt. Sandstone, limestone, and clay are the major types of sedimentary rocks. Schist and slate are the major types of the metamorphic rocks. Most rock forming minerals are silicates, compounds of oxygen, silicon, and other elements. Rock properties can show extreme variations. It is useful to generalize as in the table below in order to build an understanding of geology, but it must be accepted that rocks are not engineered materials and their properties do vary from site to site. For example, most sedimentary rocks are quite weak, and limestone is a sedimentary rock, but some of the limestones are very strong. Thank you so much for watching the video. 谢谢大家。